Welcome back to another episode of Fool's Lore. In this episode, we are going to be talking about how logic gates can be used to make neural networks, machine learning algorithms, and perceptrons, and how these neural networks are used to make the AI models that we use every day. Welcome back to Fool's Lore, and in this episode, this is going to be a banger of a episode. So again, this can be a long one because that one seemed to do well, so I'm going to make another long episode, but this one's going to be about neural networks and how can we make a perceptron out of logic gates. So first of all, let's define what a perceptron is, and the definition I'm going to give it is like the basic unit of a neural network. And that is very vague, but we're going to see how to make one, and hopefully that clears it up in the future. But a neural network is something that can be given a set of outputs that we want it to have, and then it learns how to get those outputs from certain inputs. For example, let's say we showed a computer a picture of a dog, and we said, this is a dog, and like remember what it looks like. Then we showed it a picture of a cat and said, this is a cat. Remember what it looks like. And we did this 1,000 times. So it has 1,000 pictures of dogs and 1,000 pictures of cats. And now if we put a random picture of a dog in front of it that it's never seen, it should be able to learn what a dog looks like and be able to classify it by itself. So it can learn the outputs that we want from given inputs. But we're going to look into the math behind perceptrons first, and then I'm going to show y'all how we can make this math a reality with just basic logic gates that we've been using in the simulation before. But I'll give y'all a little snippet of what it looks like real quick. So this is the perceptron that I made. This is it learning. So there is a learning algorithm that I've developed. It might already exist, but I don't know yet. I came up with this answer on my own. But this is it learning right now. But let's look at the math real quick so we fully understand what this perceptron is trying to do. So this is an XY coordinate system. You can see we have these, the x-axis and the y-axis. And we have these two variants of data that we are given. We have the circles, or the dots, and the triangles. So we can use a perceptron to classify these two types of data. And using just math, we can make a line. We can make a line equation that easily separates this data, right? So if there's a dot, a point on this graph, let's say right here. So this is 3, 2. So if we give 3, 2 to the perceptron, it's going to predict that it should be a triangle because of this line equation that we are going to give the perceptron. So there's lots of good videos on YouTube that explain the math really well behind this. So if I don't do it justice as it deserves, you can go watch one of their videos. But we're also going to go a little bit deeper into this. So make sure you understand the math before we keep going further. But I'll try to reiterate it. So we can give the perceptron a line equation, and once we give it a coordinate, it can predict what the outcome should be. That's basically what it's doing. But it can only do it for linear line equations. So, if you remember high school algebra, you have y equals mx plus b, and it can only solve it for equations like this. So let's say there was triangles, all over the place, like this. It can't make a line that like swerves in and try to like isolate the triangles like this. It can't do that. So only linear equations can be solved by the perceptron. But I don't know where you are in your learning curriculum for school, but if you know what polar coordinates are, we can do something fancy with that to get the equation. But let me explain what polar coordinates are real quick, just for the people who have no idea what I'm talking about and think I'm a crazy guy. Okay, so this is our little graph, right? So normal coordinates, they're called Cartesian coordinates, is you move X amount of distance from the origin uh, on the x-axis first, and then you go up on the y-axis, right? So like 3 comma 2, you move 1 2 3 1 2 right here, and this would be 3 comma 2. That's a Cartesian coordinate. So for a polar coordinate, we were given the radius first and then the angle. So for example, let's say that there's this line coming out of the origin like this, and we'll say it's 5. It's 5 in distance at this point, and it's at the angle of, I'll say 60 degrees. So we can write this as a different coordinate system, and it's called polar coordinates. So we write 5, 60 degrees, and that's the coordinate system. So instead of going across the x and the y-axis, we had this radius, and then we had the angle at which the radius is corresponding to the origin. And so this can also give us a linear equation in polar coordinates. So we can also get theta equals mr plus b. Instead of y equals mx plus b, we get this. And this allows us to make a different perceptron that can solve this. Because polar coordinates is all about radius, which is about circles. So we can make a linear equation in polar coordinates that's a circle around these inner dots, and it can separate these inner dots from these triangles, which is kind of cool actually, because I just learned about polar coordinates in my calc class, and now it can be applicable in computer science and electrical engineering and neural networking. So this is one application that we can do with this, and we can use this in neural networks in order to make a perceptron learn, and it's still considered a linear equation. But my perceptrons won't be using this polar coordinate system just because I had no really use for it yet of what I wanted it to be coded to do. So there was no need, but it is possible. Okay, but anyway, let's just get back into the simulation right now, and let's make the perceptron. Let's make it. Okay, so welcome to the simulation, and we already discussed really the math behind perceptrons and how they work on a mathematical level, but how can we make this out of logic gates? And that is the core concept of this YouTube channel. How can we make stuff out of logic gates? So if you look on YouTube, you'll find a lot of videos about the math behind perceptrons, but nothing tells you how to make a AI model with logic gates, because at the end of the day, that's really all ChatGPT is, and OpenAI. It's just computers with this awesome algorithm in them. So how does this work? So we're gonna have 4 models of our perceptron, and each model is gonna get more and more advanced. But this one is what I'm calling the most basic model, because we just add up the inputs and then we subtract it by a bias, and that's exactly all it is. Since the inputs are binary, we don't really need to multiply by anything just yet, and we'll see how this can change with future models. But this model right here can tell us if 3 or more of these inputs are on at any given time, and that's just given by this standard what do you want to say, standard algebraic equation. So and I'll put it up on the screen right here. It's pretty standard. It's y equals x1 plus x2 plus x3 plus x4 minus 3. And we have the 3 right here. Let me see. Yeah, so we have 3 right here. And this is our little subtract signal for our ALU. So we have one input on. You see the output doesn't come on. But if 3 are on, and it can be any 3 in any variation. If 3 are on, the output comes on. And if 4 are on, the output is off. Oh, the output is off. And then we can change the output right here to kind of determine what we want. So if it's this one, it's 3 or more. Then you see. Okay, that's my bad, guys. So let's look a little bit under the hood of this ALU because it's slightly modified. We had the little subtraction that we always have. Over here, so we have this little logic system that lets us know if the output is 0. And then this one right here allows us to know if the output is positive or negative. And that really helps with this little slope equation because we can know if the equation is above or below the x-axis, which that determines if it's 3 or more. But if we want it to be exactly 3, then we use is it 0, because then we just have 3 as the input and then 3 as the bias, and that subtracted will give us 0. So I'll put this in real quick. 3, right? We go in here, it's 0 right here. We have 3 as the inputs, and then we get the 0 output, and 0 is considered, look, this might be a little controversial, but 0 is considered positive. So if it's on the x-axis, this still gets lit up, and if it's over, then it still gets lit up. But if it's negative, this does not light up at all. And that's just kind of the way how subtraction works in computers, because we chain up these full adders. So this one's lets us know if we're in the positive or negative range, which is cool. So that is the first model of our Perceptron. A little baby model, really. So let's go into the second one. So this is the second model. And this one, it's a little more complicated. You can see we have these multiplication units. So now we're kind of multiplying by the inputs, but it's not a complicated multiplication at all since it's still a binary input. So literally the input is either going to be like 0 or whatever the number is being multiplied, because it's being multiplied by 1. so not too much is happening. This one allows us to know if the number is greater than or equal to 5. So you see if it's 4, the light is off. If it's 5, it's on. 6, 7, on. 3 and whatnot. So that does help with that. And the way this equation is set up is y equals 4x times 4x1 plus 2x2 plus x3 minus 5. And you can see that kind of right here. Right, so this top multiplication unit, binary 1 going in here, and then we have multiplied by 4, so the output is either 0 or 4. This one's either 0 or 2, and this one's either 0 or 1. So not too complicated of multiplication happening, and then we just add up all the numbers, and then we subtract it from the bias. So again, not that hard of one, but we do have this little multiplication layer to make it a little more complicated, and we can see how this works. Yeah, the same thing over here is a positive, and if it is, we light up the output. Not hard, not hard. Let's go to this one. I don't know what I changed. That's fine. So this one's a little more complicated too. This one, we don't have a multiplication unit in it, and this is the third one. So the way it works is if one of these columns is fully lit up, the output is on. And it doesn't matter what any of these other inputs are, but if another column is lit up, then it becomes off. So the output is only on if at least one of these columns is full and another one is not, which is kind of complicated. Let me see how I describe this real quick. Oh yeah, so we're gonna add up these numbers again, subtract from the bias, just like the first Perceptron we made, but there's 3 of them. So, but then we add up the numbers and subtract it from another one with a bias, but we're not adding a number. We're seeing if it's high if the positive is high, so let's look at this one real quick. So all three of these are added together. Gives us 3. 3 minus 3 is 0. And as we know, 0 is considered positive, so it lights up the positive one. And then this is an input to another adder. So then it gets fed into this bias, which is just 1. This bias is just 1. So 1 minus 1 is 0, which lights it up. And this one is being lit up on is it 0 or not, and not if it's positive. So it lights this one up. I hope, excuse me, I hope that made sense. That was really complicated. So again, I'm going to say it again. We have these 3 inputs. They're being added together. They go into this ALU, and we subtract it from the bias. So 3 minus 3 gives us 0, which is positive. And then the positive outputs get fed into this one adder, and we add them up. And if the output of this adder is 1, then we send the final output as high. And the way we determine or know if the output of this adder is 1 is we just subtract it from 1. So 1 minus 1 is 0. And this output lets us know if it's 0. Okay, so hopefully that made sense. And each of these are connected to their own. I'll put up the equation on the screen, but in my opinion, the equation does make it harder. And I'm not saying this equation because it's pretty long. It's a long equation. So that's it. Let's go to the next one. The next one is the fun one, the learning one, the learning perceptron. Okay, so now we are in the learning algorithm one, and the way this works is kind of interesting, to say the least. So we have these inputs. Each of these inputs is its own. So don't think of this as a 3-bit number. Think of this as just 3 inputs. And then we have the output. So let's say we only want the output to turn on if all 3 of these are lit up. Then we turn on the learning algorithm, and it learns. So now it only turns on when all 3 of them are on. Let's say we want it to turn on when 2, doesn't matter which 2, but when 2 of the inputs are on. We turn on the learning algorithm, and it learned. It learned. So now when 2 of them are on, doesn't matter what 2, the output becomes on, but anything else, the output is off. So how does it know? How does it learn? So the way that this little neural network works is the learning algorithm is obviously hooked up to a clock, and the clock's hooked up to these this little AND gate circuit right here that comes from the output, and basically it kind of brute force the bias. So what we're doing is we're just adding these numbers, subtracting from the bias, just like the first circuit, but we have to figure out what we want the bias to be. And since this circuit is so small, we can kind of be like, oh, the bias should be 2, because 2 minus 2 gives us 0. But it doesn't know that. So it literally tests every number, and it stops on the number that makes the output high. So we can see that if we test for, let's just say we want 1 to be high. It's testing every number, and it's seeing what number makes this output high. And whatever number makes this output high, we're going to stop the little input system into our learning mechanism. And then it gives us what the correct bias should be, which is pretty cool. And the little learning mechanism is really easy. It's just a program counter. And I mean, this is complicated, but look at the program. Look, trust me. Look at the program counter episode if you're curious. But all this does is it just increases the number by 1. That's what a program counter does. So it's just made with JK flip-flops. And then every time the clock signal is high, we just add 1. So it's an easy way for us to test all possible numbers, binary numbers possible. And then we have the deregister, which really isn't necessary. I don't know why it's in here. but it is, and it kind of just saves a number. But this also can save a number, so it really is unnecessary. But this is how this is how my brain worked making it. So we're keeping it in this design, and it works. So again, I'll show y'all. Let's just say we want the output to be high when it's off. So it learns, it tests every number, every binary number. So 13, 14, 15, and 0 is the number that it works for. Cool. Very cool. So now we know how to make a learning, I'm trying to see what this is, a learning perceptron. Let's go into this one. This one is significantly more complicated. This is the most complicated one we're going over today. And oh man, this one's take up like most of the episode. This is about to be an hour episode. So the little intro, or I don't know where I'm gonna put this video at. Might put it right here actually. But this is a time lapse of it learning, and the algorithm that we want it to learn is the one that we've like already done, kind of, is if 2 of them are on, or if all 3 are on. And there's actually multiple ways you can solve this, but just like the second perceptron we have the multiplication units, we add them up, and then we subtract it from a final bias. So easy. I hope this is very followable. But if we look at the one right here, you can see that this is just a multiplexer. So just so it can either go into, you'll see in a second. So it's just a multiplexer, right? So we have one, middle one, and the bottom one. But if we look at these, right, I'm just going to highlight one. The output goes into 2 adders. So I'll put up a little blender model right here, but instead of the second perceptron, which fed one output into one like multiplication unit, now we're feeding 2 outputs into 2 multiplication units. And this allows the network to be more like picky about the unique combination of numbers that we can have. So instead of multiplying a weight by 1, we can multiply it by 2. We can multiply by 2, we can multiply by 1 or 0. It gives us more combinations of weights, I guess you can say, more variance. And the way that this works is you select, oh yeah, okay, so this is kind of like set up as a 3-bit binary number, but it doesn't necessarily behave like it. So you select what you want high. So for example, when the number is 7, we want the output to be high. And that's kind of what I'm saying right here. This is the training model right here. So if the output is high for the number 7, we train it. We're pretty much telling the model, like, when 7 is on the board right here, we want the output to be high. And do whatever you can to make the output high. And then same thing for 6. So when the number is 6, we want the output to be high. So mess with any of the weights you can in order to make the output high. And the same thing for 5 and 3. And give you a little visualization of what it looks like. So this is 3. So we're pretty much saying if 2 or more lights are on, make the output high. Same little thing we have over there. Okay, and that's our learning button. It just syncs the clock up pretty much with this. And then these right here are count registers, which is pretty much just a program counter, like we've seen in the last learning perceptron model we have. It's just a program counter, so it can cycle through every variant of numbers in order to pick one that works. So hopefully you could see the major flaw in this. If not, then I'll explain it right here. The way the model learns is it tests every variation of number possible. So, I mean, it's kind of crazy. So, it's a 4-bit system. So, there's 16 possible numbers. So, 16 times 16 times 16 16 to the fourth. I don't even know what number it is. I think it's like 64,000. But that's how many different variations it has to test at maximum to get at least the correct one. Because it tests every number possible. So the way it works is this right here, and I'll explain in a second, tells us if the output equals the desired output that we programmed it corresponding to the number that's present on the board. And if it doesn't equal the same, then it outputs this as high. And when this is high and the clock is high, we send a update to our program counter and it adds 1. And then we test that out with all 7 bits. And if this one has a flaw, then we update it again so it can add another one. And then once we add this all the way up, so like past 16, then we add 1 to this register and we do the same cycle. And then once this one gets all the way up to 16, we add 1 to this one. So it's kind of like a big gear reduction circuit. That's like the best analogy I can give for this. This is a big gear reduction circuit. I'll play it right now. So, and this right here is a little program counter. So for every clock cycle, we increment it by 1. And that allows us to test all the variations. All 8 of these. So actually it's 16 to the 4th times 8. That's how many possible variations we have to test. And then once the circuit is correct, this output should never become high. So it should match everyone. Actually, let's look at this real quick. So this is also very complicated. We have a decoder right here. Simple decoder. So we take 3 in and we get 8 out. So if we're in a certain number, so right now we're in the number 4, so the 4 pin is high. And then we have a little comparator right here. So we compare, is the output from the the main output, is it the same as what we want it to be? And if it is, then we don't output anything at all. And so this becomes low. And then we have this little D-latch circuit right here just to keep everything in sync so we don't get any stray like highs. And we had this AND gate right here because let's say we're in the number 4. So we want this 4 pin to go out. And then we want the 4 pin right here to also be out. And so we can make a decision on whether or not these two match. And these two do not match. So the output is high. And we have a NOT gate too because we have to inverse it. So the output is high in order to update everything. So I'm going to put the little learn circuit on. We can see how it kind of like works. Okay, so I'm going to explain what's happening right here. So after we saw how it works, so the number 4 is going into our little full adders right here, correct? And it's being, added up, multiplied by the little circuit, and then we're outputting high. Okay, we're outputting high with the current weights being held in the registers, in the little counter registers. So we send that back into our coder, and our coder compares the 4 right here to the 4 output that we get. So we program this thing to output low for 4, but we're outputting high. So the coder then outputs this as high. In the next clock cycle, we're going to update the bias by 1, and we're going to see if that fixes it. If that does not fix it, then we're going to update the bias by 1 again, and we're going to test that. And then once the bias gets over 16, we add 1 to the first weight in the multiplication unit, and we test all the biases again. And once all the biases are tested again, we add another 1 to the first weight. Then once we test all variants of the first weight, we add 1 to the second weight. So that's exactly what's happening. So I'll give it a little, I'll time lapse this a little bit to see. But the video that I either showed earlier or whenever, I got a good recording of that, so it won't take too long for it to solve the algorithm. And there's different ways, there's actually a few ways to solve this algorithm. It's not just one way. Okay, so notice how the output is no longer becoming high from the coder. So that kind of signifies that the output that we're getting from the model matches what we coded it to do. So the algorithm is done, the learning code is off. We can turn off the load feature, and now we can test it. So this goes from, learning mode back to normal mode, which I guess I can hook this up directly. Look at this. Now it's gonna be a little cooler. Yeah, so let's test it, right? So look, 0 is off, good sign. 1 is off, 2 is off, 3 is on, which is what we coded it to be. 4 is off, which is good. 5 is on, 6 is on, and 7 is on. So it learned exactly what we trained the model to learn, which is super cool in my opinion. And this is how AI is made. This is literally how Chat GTP is made, using, I won't say this exact model because this coder right here is completely my design. I kind of just thought of it myself. It might actually exist, and if it does, that's cool. But I don't know. But it's the same premise. You know what I mean? You have to train the model. You run it so it can learn, and then once it learns, it can update other models, which is exactly what we did right here. So, yeah, and look, the solution is, this is the number. This is 6. This is 3, 2, and 2. So those are the weights. It also works. All of these are 1, and then this is 3. So that's also a way that it works, which is what we saw in the second Perceptron. I don't know if you remember it, but that was how that was its solution, kind of. Was it the second? It might have been the third one, but whatever. Yeah, I mean, I don't know what else to say about this. And the only thing really to upgrade on this would be to, it's like automatically turn itself off once it learns the algorithm, but I did not want to make that because that would be a complicated circuit. But anyway, that is it with this. I'm pretty sure this is going to be the end of the episode. We're like probably a solid 30 minutes in. If I had to guess, I don't know right now because I filmed these in different segments. But thank you for watching. Please subscribe if you want to see more, electrical engineering content, especially about this, because look, normally I say I'm the only one making transistor computers, which I'm wrong. There are people who are making it who reach out in the comments to me, but now I can say I'm the only one making a neural network with logic gates that I know of. So hope this was very informative, and let's subscribe and let's grow this channel.